In this section we will discuss about renewables, and in this particular lesson we will be talking about PV power or the solar photovoltaics. So let us go to the concepts. In this lesson we will discuss about various terminologies of the PV panels that are used, and we will also look at how to design a grid-tied PV system. And finally we will look at how to implement the grid-tied PV inverter in the ETAP environment. So here we will go through the basics. I am not going to explain about the basics of solar photovoltaics and how power is generated using photovoltaic effect and so on. Here we will discuss only about the terminologies that are used in the design aspect. So the standard test conditions are the test conditions that is used to rate a PV panel. So PV panels voltages, currents, the power and its efficiency are rated on the standard test conditions. So here we have the panel ratings over here. We have the VOC, which is called the open circuit voltage, the ISC short circuit current. So the voltage and the current are rated based on this test condition over here. And we also have the kilowatt peak or the watt peak, which is the power in peak, which is corresponding to the power that is generated during this test condition over here, and this is the efficiency. And then in the design we will discuss about how to design a grid-tied PV system. So the energy put into the grid is given by whatever PV, and the energy drawn from the utility or the grid is given by whatever load. So we will have different tariffs for the energy from the PV as well as the grid. So this is given by CPV and the C load. So in order for the net cost to be zero, then the energy which is to be provided by means of the PV system should be equivalent to this particular equation over here. So for the net cost is zero, that is we do not pay anything to the utility in this case. So the amount of energy that is required to be generated is given by WHPV. So next we will look at this example over here. At present I do not know the required amount of energy from the PV system, but I do know the load, which is 400 over here. So the energy is 400 kilowatt hour, and I do know the tariffs over here. So for simplicity I have kept this at the same values of $1 per kilowatt hour. So the net cost is zero when the energy from the PV system is 400 kilowatt hour. So here we have the per day energy requirement from the PV system over here. So this is 400 by 30, that is equal to 13.4 kilowatt hour per day, and the peak rating of the PV system is given by this equation over here, that is kilowatt PV rating divided by HAT minimum. So the HAT minimum is called the minimum insolation level, which is given in kilowatt per meter square per day. This is also given in hours. So when we divide these two quantities, we get 13.4 divided by 4.2. This value depends upon the location of the installation and is available in the geographical tables as well. So the peak value of the PV system is about 3.19 kilowatt. So we have the peak power, and next we will have to compute the number of panels in series and the number of panels in parallel. So here we have a string. So in the string we get a number of panels in series, and the number of panels in parallel is the number of strings in parallel. So the number of parallel cells on the number of series cells is computed over here. So the number of panels in series is given by the voltage of the array divided by the open circuit voltage. So the voltage of the array is dependent on the voltage input of the inverter that is being used. So in this particular example I have used 1000 volts, and thus we get 35 panels in series. So in order to compute the number of panels in parallel, we will have to obtain the current from the array. So the current from the array is given by the power divided by 0.85 times the open circuit voltage of the entire array, which is given by this term over here, VOCT. So that is equal to 4.11, and the number of panels in parallel is given by the current of the entire array divided by the short circuit current. So that is about 0.47, and I have rounded all these values to the next closest integer. And so the total number of panels that will be required is about 35 panels. So 35 into 1, that's 35 panels. So the total area of installation, is about 1.3 times the entire area of the panel. So the number of panels into the area of one panel gives the total area of the panel. The 30% additional is used to take care of the shadow effects and other effects, etc. And let us assume that the area of one panel is 1 meter square. So the total area is 1.3 times 35, that is 45 meters square. So sometimes in the design problem you will be given only the total area of installation, so you will have to determine the amount of energy you could produce by the particular given area. Now we will enter into ETAP and we will look at how to implement this in ETAP. So here we are in ETAP, and in ETAP I have already configured the single line diagram over here. We have two grid tied inverters over here, two grid tied PV inverters over here, and we also have a utility that is connected via a transformer over here. So the example values that is used over here is based on this Excel sheet over here. So from this Excel sheet you can see that the HAT minimum is obtained for 5.2 kilowatt per meter square per day, the area of the panel, the kilowatt hour load. So here the kilowatt hour load is 1000 kilowatt hours, and the tariff is the same, and you can see the energy per day requirement is 34 kilowatt hour, and the kilowatt peak rating of the PV system is 6.54 kilowatts. And here we have the same calculations. The voltage of the array, the number of panels in series is 31, the number of panels in parallel is 1, so the total number of panel is 35. I will provide this Excel sheet in the renewables. So let us go to ETAP over here, and in ETAP you can implement grid tied inverters in two different ways. Here the inverter is inherent to this module over here, whereas here we will have to provide the inverter separately. So this is available from the AC toolbar over here. You can see here we have the PV array, and this PV array is similar to that of this PV array but as a separate inverter block over here. So this does not have an inherent inverter, so this is available in the DC toolbar as the PV array option over here. So this is the PV array over here. So you will have to connect this to a DC bus and then to an inverter over here. So let us go to the configurations over here. For the PV array editor, we will have the info tab, and we will also have the PV panel over here. So I have chosen the Q cells 230 watt panel. I have used these values for my calculations, so I have chosen this panel, and we will go to the PV array. And from the PV array we get the watt per panel is fixed, we cannot change this, and we get the number of panels in series. I have provided this 35 as from the Excel sheet values, and the number of panels in parallel is 1. So here you can see the PV array total values. So the number of panels is 35, the DC volts is about 1000 volts, the DC power is 8.025, and the DC amps is 7.82. And then we will have to go to the irradiance calculator over here. So this calculates the irradiance watts per meter square, and we will have to provide in our local time, the date, etc. And by providing in the latitude and the longitude values over here, you get the irradiance over here. So we get the equation, the solar altitude, the solar azimuth, and so on, and you also get the irradiance. So at this particular time of the local time, so the irradiance is 297. So let me provide the noon time over here. So we will have to put this in AM. So we get this irradiance of 889. So I will update all these values over here, and you will get these values over here. And we have the MPPT of kilowatt hours. So you will have to check this box over here. This is the maximum power point tracker. This is an algorithm that is used to extract the maximum power from the PV system. So then we will have to go to the inverter tab over here, go to the inverter editor and provide in the ratings for the DC, and correspondingly the AC ratings will be updated over here. And in the DC generation page you will have this will get updated as per the radiance calculations. So let me close this over here and click this on OK. So let me conduct a load flow without our grid-tied inverter systems over here. So you get the 6 kilowatt hours of power is flowing from the utility to our system. So 6 hours into the duration of 6 kilowatts into the duration gives us the energy requirement. So now let me close this system over here and let us run the load flow analysis. So you get the 6 kilowatts of power is flowing from our PV array over here, and this will be available for a period of 5.2 hours per day. So when you perform the calculations you will get about 936 kilowatt hours of power for an entire month. And next we will do this using this PV array over here, and for this particular PV array you can provide number of panels in parallel as well. So the same number of panels are provided in series and in parallel, and let me provide in the latitude and the longitude values over here. I'm going to provide in the noon time 12 AM, and let me put this on calculate. So you have the air mass value and the radiance values over here. I'm going to click on update all, and then I'm going to click on OK and go to the inverter, providing the ratings over here and here. And in this DC generation page you will have to provide in these values of AC from the inverter itself. So I have already provided in 6 kilowatts of power in this case, and when I close this over here you will get about the same kilowatts of power from this grid-tied PV as well. So this is how we can implement grid-tied PV systems over here. And let me show you something else. So in the PV panel the ratings are already provided over here. So you get the VOC, the ISC, and the VMP and the IMP are the power at the maximum power point. So this is the maximum power point. So these values are this is the IMP value, this is the VMP values, and the fill factor is just a benchmark that is used to indicate the quality of the PV panel. So in this lesson we have gone through the basics of PV systems and the design of PV array, and we have also seen how to implement grid-tied PV systems in ETAP. So in the next lesson we will discuss about wind turbines, and I will see you in the next lesson.